Suppose I told you that engineering calculus 2 is less about more calculus and more about learning to see shapes, motion, and change from the right angle. Because once a few key perspectives click, the subject becomes much less random. Suddenly, topics that felt disconnected start to feel like they belong together. In this video, I will show you 5 angles that can make Calculus 2 finally make sense, not just in theory, but in the kinds of engineering problems you will actually use later. The first angle is probably the most famous, area under a curve. But in engineering Calc 2, this isn't just about finding a number between a graph and the x-axis. It's about accumulation. That means if something changes little by little, like flow rate, force, charge, mass, or work, calculus can add up all those tiny pieces into one useful total. For example, if water flows into a tank at a changing rate, integration tells you how much total water entered over time. That's why integrals are everywhere in engineering. They turn rate into total. The second angle is to stop thinking of an integral as one big thing, and instead think of it as many tiny slices. This is the mechanism behind why integration works. You break a complicated shape or process into pieces so small that each one is easy to handle. Then you add them all up. This is useful for things like volumes of oddly shaped tanks, center of mass, and work done by a variable force. For instance, if a spring gets harder to stretch the farther you pull it, the force is changing. So instead of using one simple formula, you add the work from each tiny stretch. That's the real power of calculus. It handles non-constant reality. The third angle is symmetry. Many Calc 2 problems become dramatically easier when you notice what repeats, mirrors, or cancels out. In engineering, symmetry can save time, reduce computation, and even help you check if an answer makes sense. For example, if a shape is perfectly balanced left to right, the center of mass should land in the middle. If your result says otherwise, something is probably wrong. This matters because engineers don't just solve problems, they verify them. Symmetry is one of the fastest ways to build intuition and catch mistakes. The fourth angle is approximation. Much of engineering Calc 2 becomes practical when you realize that exact answers are not always the goal. Often, the goal is a good enough answer with known error. That's why sequences, series, and Taylor approximations matter. They let you replace messy functions with easier ones near a point. For example, in computation or modeling, a complicated expression might be too expensive to evaluate directly, but a Taylor polynomial can give you a fast estimate that's accurate enough for engineering use. This is basically how calculators, simulations, and control systems often think. Not perfectly, but usefully. The fifth angle is motion. Calculus too often feels static on paper, but its ideas are built for dynamic systems. You're studying how quantities build up over time, how curves behave, and how repeated change creates structure. That's why the subject connects so well to fluids, signals, mechanical systems, and electrical engineering. A current can vary, a beam can bend, a signal can repeat, a system can accumulate error. Calc 2 gives you the language to describe all of that. So if Calculus 2 feels overwhelming, don't just memorize formulas. Try viewing the subject through these 5 angles: area, slicing, symmetry, approximation, and motion. When you do, the course stops looking like a pile of unrelated techniques and starts looking like one toolkit for understanding the real world. And that's the part worth remembering. Calc 2 is not just about solving integrals. It's about learning how engineers measure, estimate, and model the continuous world. Engineering Calculus 2. 5 angles that make the subject click is just one small part of Calculus 2. If you're interested, our full free Calculus 2 course is linked in the description.